In this lecture, we talk about the heat and the heat capacity. Heat, often denoted with Q, is a form of energy that can be transferred from one object to another. If you want to know how the heat is stored in the object before transferring, you have to focus on the physical property of the object. The object that you are interested in is usually called system. The object other than the system is called surroundings. Suppose that hot water cools down by heat releasing into the air. In this process, if hot water is the system you are interested in, then the air around is the surroundings. Heat transfers from the system to the surroundings through a boundary, the wall of the bottle. The wall here permits heat transfer, is diathermic. If the wall does not permit heat transfer, the wall, or precisely the boundary, is adiabatic. There are three types of systems named open system, closed system, and isolated system. In the open system, matter and energy, heat for example, can be exchanged with the surroundings. Imagine a bottle of hot water without a cap. Water and heat can go out of the bottle. In the closed system, only energy, not matter, can be exchanged with the surroundings. The bottle is capped, no water in or out, only heat emits. And in the isolated system, no exchange occurs. A capped thermos, both heat and water are locked down. How can the water store the heat? Why does the temperature go higher if the water is heated? It would be preferred that explaining the heat storage and transfer at the molecular level. Imagine that water molecules are heated up, then the kinetic energy of the molecules increases. Or say the molecules moves faster than ever. The vibration of the bonds in the molecule increases, which can be considered as potential energy. Then the internal energy, the sum of kinetic energy and potential energy, increases. The heat absorbed by the system, the water, is stored in the water in the form of internal energy increases. The heat capacity, denoted with a C, is used to characterize the ability that a substance stores heat, defined as the amount of heat to raise the temperature of a substance by 1 degree C or K. For example, the molar capacity of water is about 75.3 joules per Kelvin per mole. Indicates that if temperature increases 1 K, 1 mole water will absorb, or say, can store 75.3 joules heat. If you want to know how many heat is stored for n moles water with the temperature increase of delta T, then you can use the equation shown here to calculate. For convenience, we usually plug a sign in front of Q value, either plus or minus. If Q is positive, with plus sign, it means the heat is absorbed or stored by the system. If the sign is negative, it indicates the heat is released out from the system into surroundings. For example, if 1 mole of water releases 75.3 joules heat out into the surroundings, it's written as Q equals minus 75.3 joules. Clearly, The sign in front of heat indicates the heat gain and loss of the system. Let's solve a problem so that we can understand the concepts better. What is the final temperature of water when 0.05 moles of ice at 0 degrees C is added into 0.045 moles of water at 25 degrees C, assuming the process occurs at a constant pressure? In this process, ice will absorb heat to become liquid water at 0 degrees C. We say phase change from solid to liquid. Then the liquid at 0 degree will further absorb more heat to warm up till the temperature is the same as the water bath at T final. Heat Qi is absorbed, and Qi includes Q1 heat for phase change and Q2 heat for warm up. While the water bath will give off heat to warm the ice, warm the water from ice up till no heat exchange between. The heat transferred total is QW. But there is a minus sign. Because the heat is released, we then have minus QW equals QI equals Q1 plus Q2. Then the equation is further expressed by moles times the heat capacity and temperature change, T final minus T initial. Plug the values into the equation. Finally, we have T final is 11.58 degrees C.